This is a recast of the 7,500-word piece, Graph Neural Networks, GNNs, from Schneepat.com. This article discusses the importance, advancements, and applications of graph neural networks, GNNs. GNNs are a powerful type of neural network that can effectively capture complex relationships and dependencies within graph-structured data. They have been successfully applied in various fields such as medicine, business, natural language processing, computer vision, and more. GNNs offer advantages over traditional methods in terms of modeling complex relational data, flexibility in handling different types of graphs, and the ability to learn informative representations from raw graph data. However, challenges such as scalability and interpretability still need to be addressed to fully harness their potential in real-world applications. Ongoing research efforts are focused on developing scalable and interpretable GNN models to overcome these limitations and enable widespread adoption. Let's listen in.
Today, we're diving into the fascinating world of artificial intelligence and neural networks. Specifically, we'll be focusing on a type of neural network called the graph neural network, or GNN. But before we get into that, let's lay some groundwork by briefly explaining the importance of neural networks in various fields.
That's right, Paul. Neural networks have become incredibly important and popular across a wide range of industries because they can mimic the functionalities of the human brain. In the field of medicine, for example, neural networks have completely revolutionized disease diagnosis, prediction, and treatment. By analyzing large volumes of data, such as patient records, genetic information, and medical images, neural networks can accurately identify patterns, predict outcomes, and even recommend personalized treatment plans.
Absolutely, and it's not just in medicine. Neural networks are also essential in the business sector for tasks like customer behavior analysis, fraud detection, and demand forecasting. By processing vast amounts of data from multiple sources, neural networks provide businesses with valuable insights to make informed decisions and improve operational efficiency.
Well said. And in the field of natural language processing, neural networks have played a crucial role in developing advanced language models, speech recognition systems, and machine translation algorithms. Not to mention their extensive use in computer vision, recommender systems, autonomous vehicles, finance, and many other domains.
Exactly. The versatility and capability of neural networks to handle complex problems have positioned them as an indispensable tool in a wide range of disciplines. And with continuous advancements and applications, neural networks hold great promise for the future.
Now that we've explained the importance of neural networks, let's move on to discussing the advancements in neural network techniques. One notable development is the graph neural network, or GNN.
That's right. GNNs have revolutionized the field of deep learning by incorporating graph structures into the learning process. Traditional deep learning models like convolutional neural networks and recurrent neural networks are fantastic at tasks like image recognition and natural language processing. But they struggle to effectively capture and model complex relationships in non-Euclidean domains like social networks, molecular structures, or recommendation systems.
GNNs overcome this limitation by leveraging the inherent structure of graphs. They achieve this by propagating information across the graph through a series of message-passing iterations. Essentially, nodes in the graph exchange information with their neighboring nodes, allowing GNNs to capture hidden patterns, global structures, and higher-order dependencies in complex networks.
And the success of GNNs has been demonstrated in various applications such as graph classification, node classification, link prediction, and recommendation systems. These advanced neural network techniques have opened up new avenues for researchers and practitioners in the field of deep learning.
Absolutely, Paul. GNNs are a powerful and versatile class of neural network techniques that have gained significant attention in recent years. They're designed to process and analyze non-Euclidean structured data like graphs and social networks. And they've shown great success in a variety of domains, including social network analysis, recommendation systems, and even drug discovery.
One of the key features of GNNs is their ability to handle irregular and dynamic structures. They can incorporate various forms of information, such as node attributes, edge weights, and temporal information. This makes them particularly well suited for tasks that involve complex relationships and dependencies between entities in the graph.
Absolutely. GNNs offer tremendous potential for solving complex problems involving structured data. They're an exciting area of research in the field of deep learning, and we can't wait to see what new advancements and applications will emerge in the future.
Definitely. One of the main advantages of GNNs is their ability to capture both local and global information within a graph. Traditional neural networks primarily operate on grid-like inputs, but GNNs can handle graph-structured data such as social networks, biological networks, and molecular graphs.
That's right. GNNs achieve this by using a process called message passing. Each node in the graph receives information from its neighboring nodes and updates its own features based on this information. This iterative process allows nodes to refine their representations and gain a more holistic understanding of the graph structure.
And what's interesting is that GNNs can learn from both the node level and graph level perspectives. At the node level, GNNs capture the local dependencies and properties of individual nodes within the graph. At the same time, at the graph level, GNNs capture the global patterns and relationships that emerge from the interactions between nodes.
Exactly. This dual perspective allows GNNs to learn rich representations that encode both micro and macro levels of information present in graph-structured data. This is a significant advantage over traditional neural networks that often struggle to capture complex relationships within graph data.
And it's important to note that GNNs are not limited to just one layer. They can be stacked to increase their expressive power and model increasingly complex relationships within a graph. By leveraging the rich structure and connectivity of graph data, GNNs provide a powerful framework for various applications in domains such as social network analysis, recommendation systems, drug discovery, and knowledge graph reasoning.
Absolutely. GNNs have been successfully applied to tasks such as node classification, link prediction, and graph generation. Their ability to capture both local and global information makes them well suited for these tasks, where understanding the complex relationships between entities is crucial.
Right. And when it comes to graph-structured data, GNNs extend regular neural network architectures to effectively process and analyze this type of data. In regular neural networks, the inputs and outputs are typically vectors or tensors representing individual samples. But for graph-structured data, the input consists of a graph with nodes and edges, each carrying different features or attributes.
That's correct. GNNs take advantage of the graph structure by designing neural networks that can process both node and edge features and harness the dependencies and relationships present in graphs. This allows them to capture complex patterns within the graph and generalize well to unseen nodes and graphs that exhibit similar structures.
And let's not forget about their ability to perform graph-level operations. GNNs can learn to summarize the information of the entire graph, which is particularly useful for tasks such as graph classification or regression. By recursively applying node-level operations and aggregating information to higher graph-level representations, GNNs are able to capture global patterns and make predictions at the graph level.
Absolutely. GNNs provide a powerful framework for operating on graph-structured data, representing a significant advancement in neural network techniques for tackling complex real-world problems. Their ability to capture both local and global information, along with their flexibility in handling different types of graphs, makes them a promising tool for various domains.
That's right, Avery. And one domain where GNNs have shown great potential is social network analysis. GNNs can uncover hidden patterns within social networks and predict outcomes or behaviors. For example, they can predict friendships or identify influential individuals within a social network. By analyzing the relationships between users and their connections, GNNs can provide valuable insights into social dynamics.
Definitely. And another application where GNNs excel is in recommender systems. By analyzing the relationships between users, items, and their features, GNNs can provide personalized recommendations. This is particularly useful in domains like e-commerce or streaming platforms, where accurate recommendations can enhance user experience and increase engagement. GNNs can effectively model the complex relationships between users and items, leading to improved recommendations.
Absolutely. And let's not forget about drug discovery and molecule property prediction. GNNs have the ability to model the interactions between atoms and predict the properties of chemical compounds. This allows researchers to design more effective drugs by analyzing their potential interactions with target molecules and predicting properties like toxicity or potency. GNNs have the potential to significantly accelerate the drug discovery process.
That's a great point, Paul. And GNNs have also made significant strides in the field of computer vision. By treating images as graphs, GNNs can capture the spatial relationships between pixels and learn meaningful representations for tasks like object detection or image classification. This approach has shown promising results in medical image analysis or autonomous driving, where accurate understanding of visual data is crucial.
Absolutely, Avery. The versatility of GNNs is truly remarkable. They have been successfully applied in various domains, from social network analysis to drug discovery and computer vision. Their ability to model complex relationships and capture important features makes them a powerful tool in numerous fields.
However, it's important to note that the application of GNNs also presents challenges. Scalability and interpretability are two key concerns. Researchers are actively working on developing more scalable architectures to handle larger graphs and improving the interpretability of GNNs to better understand the decision-making process of these models.
That's right, Avery. It's crucial to address these challenges to fully harness the potential of GNNs. Despite these challenges, GNNs offer great promise for advancing the field of neural network techniques and have already shown promising results in various real-world applications.
Absolutely, Paul. The successful applications of GNNs in diverse fields, such as social network analysis, recommendation systems, and drug discovery, highlight the versatility and effectiveness of this advanced neural network technique.
And with that, we've reached the end of today's discussion. Thanks for tuning in, and we'll be back soon with more exciting topics.
But before we wrap up, let's quickly recap the main points we've covered today. We discussed how GNNs have been applied in various fields and the impact they have made.
That's right. In computer vision, GNNs have been successfully used for image recognition tasks. For example, the graph autoencoders, GAE, leverage GNNs to capture relational information between images and learn low-dimensional representations that can be used for image classification and similarity computation.
And in the field of drug discovery, GNNs have shown promise in predicting potential therapeutic candidates. The DeepGen platform employs GNNs to learn molecular fingerprints and predict chemical properties of compounds, aiding in the identification of potential drugs.
Additionally, GNNs have been used in social network analysis for link prediction tasks. GraphSAGE is an example that uses GNNs to emit nodes in a graph, enabling the prediction of missing connections in a social network. This has had a significant impact on fields like marketing, where link prediction can be utilized to identify potential customers and enhance targeted advertising campaigns.
Absolutely. Now let's talk about the advantages of using GNNs compared to traditional methods in these applications.
One advantage is that GNNs excel in modeling and understanding complex relational data structures, such as social networks or knowledge graphs. Unlike traditional approaches that treat each data point independently, GNNs can capture the inherent dependencies and correlations between nodes in the graph, enabling more accurate predictions and better performance.
That's right, Paul. GNNs are also highly flexible and adaptable, making them suitable for a wide range of domains and problem settings. They can handle heterogeneous and multi-relational graphs, allowing for a more comprehensive representation of the data. And they can naturally incorporate various types of node and edge features, which are crucial for capturing domain-specific information.
Another advantage is that GNNs can learn and extract informative representations from raw graph data without requiring manual feature engineering. This saves time and reduces the potential for human biases. GNNs automatically learn high-level, abstract representations, making them more efficient and scalable in real-world applications.
Now let's move on to the challenges and limitations of GNNs.
Scalability is one major challenge when applying GNNs to large-scale graphs. As the size of the graph increases, so does the computational cost and memory requirements of training and inference. This can impact the efficiency and effectiveness of GNNs in real-world scenarios where large graphs are common.
Absolutely, Paul. Another challenge is incorporating structural heterogeneity in graphs. Graphs can have varying connectivity patterns, node attributes, and edge types, which can pose challenges for GNNs to capture and utilize efficiently. Researchers are actively working on developing robust GNN architectures that can handle such structural heterogeneity.
And let's not forget about the lack of interpretability in GNNs. Unlike traditional neural networks, GNNs lack interpretability due to their complex aggregation and transformation operations on graph data. Understanding the decision-making process of a GNN and interpreting its output is crucial for many real-world applications.
That's right, Paul. Researchers are exploring methods such as attention mechanisms and explainable AI to overcome this limitation and provide interpretability in GNNs.
So, while GNNs offer promising advancements in analyzing graph-structured data, challenges such as scalability and interpretability need to be addressed for their full potential to be realized in real-world applications.
Absolutely, Paul. Ongoing research efforts are focused on developing scalable, flexible, and interpretable GNN models to overcome these limitations and enable widespread adoption.
And with that, we've reached the end of today's discussion. Thanks for tuning in, and we'll be back soon with more exciting topics.
But before we wrap up, let's dive into some of the key points from the article. One of the major challenges in training and implementing graph neural networks, GNNs, is scalability. GNNs heavily rely on graph data structures, and as the size of the graph increases, so does the complexity of GNN computations. This poses a significant scalability challenge, especially when dealing with massive graphs containing millions or even billions of nodes and edges.
That's right, Avery. Training a large-scale GNN on such massive graphs can become computationally infeasible. Additionally, GNN training requires a substantial amount of memory to store the graph structure and associated node and edge features. As the graph size increases, memory utilization also increases, making it difficult to fit the entire graph in memory.
Absolutely, Paul. And another challenge faced in training GNNs is overfitting. Overfitting occurs when a GNN learns to model the training data too closely and fails to generalize well to unseen data. This can happen if the GNN is too complex or if the training dataset is insufficient or biased. Overfitting can lead to poor performance on real-world tasks as the GNN becomes overly sensitive to noise and inaccuracies in the training data.
To address overfitting in GNNs, regularization techniques such as dropout and weight decay are commonly used. These techniques help prevent the model from fitting the training data too closely and encourage better generalization. However, striking the right balance between model complexity and generalization ability, especially in large-scale GNNs with complex datasets, remains a challenging task.
Absolutely, Paul. Alongside these challenges, GNNs also have limitations that hinder their applicability in certain scenarios. One major limitation is the difficulty in handling large-scale graphs. As the complexity and size of the graph increase, GNNs face challenges in terms of memory consumption and computational efficiency. The iterative nature of GNNs, where information is exchanged between neighboring nodes, can significantly impact the performance and scalability of the model.
Furthermore, GNNs require labeled data for training, which can be a limitation in scenarios where obtaining labeled data is expensive or time-consuming. This reliance on labeled data makes it challenging for GNNs to generalize to unseen or sparsely labeled graphs. And labeling large-scale graphs with millions or billions of nodes is a daunting task in itself.
That's true, Paul. However, researchers are actively working to overcome these limitations through ongoing advancements in the field of GNNs. Efforts are being made to develop more effective message-passing algorithms for GNNs, refining the way information is exchanged between nodes to enhance accuracy and efficiency.
Various techniques like graph convolutional networks and graph attention mechanisms have been proposed to improve the message passing process and enable GNNs to capture more complex relationships and dependencies within the graph structure.
Absolutely, Paul. Researchers are also exploring strategies like graph sparsification to reduce the computational complexity of GNNs while preserving crucial information. This can help address the challenge of handling large-scale graphs.
Additionally, efforts are being made to enhance GNN's robustness against adversarial attacks, which aim to manipulate the input graph to mislead the model's predictions. Defense mechanisms like graph purification and adversarial training are being investigated to mitigate the vulnerability of GNNs to such attacks.
Overall, ongoing research efforts in improving GNNs aim to enhance their effectiveness, scalability, and resilience. These advancements will enable GNNs to be applied to a wide range of challenging real-world problems where relationships play a crucial role.
And with that, we've reached the end of today's discussion. Thanks for tuning in, and we'll be back soon with more exciting topics.
Stay curious and keep exploring.
Hey everyone, and welcome back to the show. Today, we're diving into the world of graph neural networks, or GNNs. These networks have seen some exciting advancements and research directions in recent years, so let's get started.
Absolutely. One notable area of progress in GNNs is the development of more sophisticated architectures that enable better modeling of complex graph structures. One such architecture is the Graph Attention Network, or GAT. GAT introduces attention mechanisms that assign differentiated weights to different neighbors during message passing. This allows the network to focus on the most informative neighbors, leading to improved performance on various tasks.
That's right. Another important advancement is the Graph Convolutional Network, or GCN, which incorporates spectral graph theory into GNNs. This provides a mathematically principled way to learn node embeddings that capture both local and global topological information. In simpler terms, GCN can capture both the small-scale relationships between neighboring nodes and the larger-scale relationships between distant nodes, making it a powerful tool for graph-based predictions.
Absolutely. And let's not forget about Graph SAGE, which introduces a highly scalable inductive method for learning node embeddings. It works by sampling and aggregating features from a node's local neighborhood, allowing it to reason about larger graphs compared to traditional approaches. This scalability makes Graph SAGE particularly useful for handling graphs of various sizes and structures.
These advancements in GNN architectures have paved the way for more accurate and efficient modeling of graph-structured data. By capturing both local and global structural information, GNNs are able to retain valuable insights from complex and interconnected graphs.
That's a great point, Paul. Traditional neural networks often struggle with graph data due to its complex nature, but GNN architectures address this challenge by incorporating graph-based operations into their design. These operations enable GNNs to model the relationships and dependencies among nodes in a graph, allowing them to capture and retain valuable structural information.
Exactly. And not only do GNN architectures capture local patterns within a graph, but they also leverage information from distant nodes using multiple graph convolutional layers. This ability to capture both local and global patterns makes GNN architectures highly adaptable and capable of learning a wide range of graph-based tasks, such as graph classification, node classification, and link prediction.
And let's not forget about the scalability of GNNs. Traditionally, GNNs have struggled with scalability when dealing with massive graphs due to memory and computation limitations. However, recent efforts have proposed GNN frameworks that can efficiently process large-scale graphs by employing various techniques like graph sampling and sparsification. This means researchers can now extract meaningful insights from large-scale graphs more efficiently than ever before.
Absolutely. And that brings us to the future directions in GNN research. One crucial area of exploration is the handling of larger and more dynamic graphs. With advancements in GNN frameworks, researchers are now able to efficiently process large-scale graphs by employing techniques like graph sampling and sparsification.
And on top of that, researchers are also investigating techniques that can handle dynamically changing graphs. This would allow GNNs to adapt to real-time updates and maintain accurate representations. These future research directions hold great promise in further advancements in areas such as social network analysis, recommendation systems, and creative ways of utilizing graph-structured data.
Absolutely. The advancements we've discussed today, such as GCN, GAT, and Graph SAGE, have propelled the field of graph representation learning. These newer GNN architectures have improved efficacy and scalability, making them a promising technique for graph-based learning tasks.
That's right. And GNNs have already shown promising results in various domains, including social networks, bioinformatics, and recommendation systems. They excel at tasks such as node classification, link prediction, and graph-level analysis. The ability of GNNs to capture relationships and dependencies among entities in a graph makes them particularly suited for these types of tasks.
Absolutely. And one of the key components of GNNs is the graph convolutional layer, which performs the information aggregation process. This layer combines node feature representations with message passing, allowing for effective propagation of information throughout the graph. Various methods have been proposed to enhance the expressiveness and efficiency of these graph convolutional layers, such as spectral methods, spatial methods, and attention mechanisms.
That's correct. And it's important to note that GNNs can also incorporate additional edge or graph-level features to capture more complex patterns and improve performance. This flexibility allows for more accurate predictions and richer representations of real-world networks.
However, it's worth mentioning that GNNs do face some challenges. One key limitation is scalability due to the quadratic complexity in the number of nodes or edges in a graph. But researchers have proposed techniques such as sampling methods and parallelization to alleviate this issue.
That's right. And another challenge is the interpretability of GNNs. Since they function as black boxes, it can be difficult to understand their decision-making process. This is an ongoing concern in the field, and further research is needed to address this limitation.
Absolutely. Despite these challenges, GNNs offer immense potential in various domains. They have already been successfully applied in social network analysis, bioinformatics, recommendation systems, and even drug discovery. And with ongoing advancements and refinements in GNN architecture and techniques, we can expect them to continue playing a significant role in solving real-world problems involving graph-structured data.
Definitely. And it's worth mentioning that GNNs are still an active area of research with many potential future directions. One such direction is the incorporation of temporal dynamics. Real-world networks often change over time, and by considering the temporal aspect, GNNs can capture dynamic patterns and predict future states of networks. Time-aware GNN models have already shown promise in various domains, including social networks and biological networks.
That's right. Another potential future direction is the handling of heterogeneous graphs. In many real-world scenarios, networks are composed of diverse node and edge types, each with its own characteristics and relationships. Traditional GNNs struggle to effectively capture and reason over such heterogeneity. Therefore, future GNN research may focus on developing models that can handle heterogeneous graphs, enabling more accurate predictions and richer representations of real-world networks.
Absolutely. And techniques such as attention mechanisms, meta-learning, and relational learning can potentially be leveraged to construct GNNs that are tailored for heterogeneity. These advancements in GNN research can significantly advance the field and lead to more powerful and robust models for network analysis and prediction.